Okay, so we are live now. Okay, so good day, everyone. We believe you are all in good health. We are about to commence shortly. We do not expect to be overly late today, but please bear with us. We might probably run maybe 10 minutes over the time. But of course, we intend to be on time and we will commence shortly.
Hello, everybody. So let's maybe wait a few more minutes so that more participants will jump in. Ciao, Lorenzo.
Hello, hello. Good afternoon, everyone.
Good afternoon. And
Good afternoon.
right. Okay, we have a good number now. Maybe we can begin. Quickly, we will let Lorenzo welcome us to the webinar event. Lorenzo Leoni is the Director of Hexagon Geosystems Mine Monitoring within the EMEA and Sudan regions. He has his PhD in engineering geology from the University of Florence in Italy. He has been in the mining monitoring business for over 15 years, and this makes him a seasoned specialist in the field. So he will give us the welcome address quickly. Thank you.
Thank you, Bilson. Thank you very much for the introduction. And of course, it's a pleasure for me to open this webinar. So first of all, hello and good afternoon, everyone. I think we can start, right? It's just a few minutes after the most important contribution will come later after my 10 minutes talk, so no problem. Well, guys, as you probably know, at the beginning of October, we organized a workshop in South Africa that was very successful, especially in terms of quality of the contributions that were shared by customer, by those that attend. Now, unfortunately, not everyone could attend in person due to different reasons that was a pity, of course, but we thought that we could still deliver, and share the message and the best practice that came out during that meeting that was in person through this webinar for a selected group of people, of course, but that could still benefit in listening and sharing this approach to monitoring. So here we are, and of course we need to thank our team that made this possible. Thanks for organizing this. Thanks both to Bilson and PDSA. Thanks to Augusto on our side here in Italy. Of course, a special thanks goes to our customers that agreed to share their presentation again today. Especially those that will be presenting later. The content of their presentation is extremely valuable, and I really encourage all of you to listen carefully and make all the questions to them. Actually, the main goal of this type of meetings, both the one in person, but even this type of webinar, is to encourage and to create a network of users that can share, experiences and best practice. So the more you can know each other, the more you can exchange feedbacks, it's the better for us. To continue growing a community of experts in critical monitoring for open pit mining with our Hexagon products, of course. So let's say that will be pretty much all on my side. again, I really thank you all for attending this webinar. I myself will listen to those presentations, and I'm really curious to hear the type of conversations that may come out, your question, your curiosity, and even, why not, your suggestion or feedbacks for improving, both in terms of approach to monitoring, but even in terms of our products, because on our side, as a developer of those technology, we value very much your feedbacks, and actually we build our roadmaps for the future following the feedbacks that are coming from the field, from real users like most of you, all of you. So let's say thank you again for attending, and I pass to the next first presenter. I don't know if Bilson or Augusto, you want to add something?
Yes. So quickly, because we are about to jump quickly into the case studies, I would like to briefly introduce all the speakers for the event. So first on the bill will be Mr. Freddie Mukolo. He is recently joined Barrick Gold Kibali Mine. He is the geotechnical superintendent with over 15 years of geotechnical work under his belt, and he will present his work on integrating early warning systems into existing slope monitoring practices. Then, right after that, we have Mr. Elisha Kanyambo. He's the next presenter, and he's the geotechnical superintendent of KCC in the Democratic Republic of Congo. He has been managing affairs there for over 14 years, and his work today will be about the case for the KOV pits, the bull nose failure. And then myself, I will be doing the work on Guardian integrations, the IBIS radar, and TPS and GNSS systems. Then finally, Augusto Melo, who is the regional sales manager for Hexagon Geosystems and has been in the radar business for about 12 years. He also has 2 master's degrees in geological technologies and engineering geology from Milan University and University of Buffalo, respectively. So he will introduce to us our recent ideas, products, releases, and updates for the year, and possibly touch on expected products and software releases in 2025. So quickly, Mr. Freddie Mukolo will take center stage and then share with us his work.
Okay. Hi, Blinkson.
Yes, hello, Freddie. We can hear you loud and clear, so please, you may go ahead.
I don't know if okay, you can see my computer.
Yes, we can see your screen now.
Yes, we can see everything. Thank you.
Okay, we are going to talk about integrating early warning systems into existing slope monitoring practices. About the introduction, increasing instability in slopes, embankments, or natural features can represent a risk. An inclination of failure in these features can trigger landslides with catastrophic consequences. Slope monitoring is a necessary requirement in any excavation process, especially in high slopes. Moreover, a high precision monitoring is imperative while excavating unstable slopes, especially to monitor slow displacements. One such high-precision monitoring system is the ground-based interferometric synthetic aperture radars. Early warning detection systems play a critical role in identifying and mitigating risk related to slope stability, allow real-time monitoring and timely alerts. How the systems contribute to safety and stability. First of all, we can use inclinometers, which is measuring the tilt and angle of slope movements, providing early warnings of instability. We can either use extensiometers, which monitoring the extension within a slope. We can also use piezometers, which gauge water pressure within the soil and helping detect changes in slope condition. We can also use radars, which are helping to detect a ground displacement in real time. What is the benefit of the early warning system? The first benefit is the risk reduction. And when we are talking about the risk reduction, we mean like early detection enables proactive measurements, reducing the risk of loss of life and property. Secondly is stabilization measurements. Alert trigger timely evacuation and implementation of stabilization techniques. And the third is the cost savings. A single increase in slope angle can save millions in stripping costs, but safety remains our paramount. Application of the early warning systems. We can apply the early warning system in the open pit mine. In mining, we can monitoring high and steep slopes is crucial for safety. We can also apply the early warning monitoring in the natural slopes. Early warning system prevent disaster in highly and mountainous region. We can also use the early warning system in infrastructure, which will allow to detect any slope instability which can affect the roads, railway, and buildings. What is the practical way to achieve the integration of early warning system? The first is the slope deployment and data collection. When we're talking the slope deployment and data collection, we means two parts. Instrumentation. We have first to install the instrumentation, such as radars, inclinometers, or piezometers, on the critical location of the slope. And secondly, we have to implement the automated data collection. And when we have to implement the automated data collection, we have also to monitor continually the behavior of the slope by displaying the displacements, maybe the water pressure in case we install piezometers. And the second way will be the data fusion and real-time analysis. All the data has to be centralized in a data hub. We can use multiple techniques to combine most of information from multiple sensors. And we can also make a real-time analysis algorithm to detect any abnormal or any abnormal trends. And the third will be the thresholds and alerts. We have to define clearly the threshold value for variable parameters. We have to define, for instance, what is the displacement rate, what is the pore pressure. When monitor a value exceeds the threshold alerts has to be implemented and has to be triggered to relevant person. It can be maybe an SMS, an email, or maybe visual indication. The fourth will be the numerical modeling and prediction. We have to integrate a numerical modeling tools such as fundamental elements or fundamental differential methods with real-time data. In case we are using radar, we can also include some software which can use a finite element to predict or to confirm what the radar shows as movement, what was the factor of safety and other aspects. And we have also to predict slope behavior based on historical data and ongoing measurements. And the fifth is the visualization and decision support. And we have to know that how the data will be visualized. We can set up maybe the maps, some displacement trends, and early warning status to engineers and makers decisions. And the sixth will be the response protocols. We have to establish a clear protocols for responding to alerts in case we have red alarm, yellow alarm, orange alarm. What is the protocols which is in place? We have also to define clearly the action based on the alert, the warning alert that you receive. What will be the action after receiving the alert? And seventh will be the training for the personnel. The personnel who will work, who will use the early warning system has to be trained. They have to know exactly how to use the system, how to set up the system, how the system can work perfectly. And also the last will be the regular maintenance and the calibration. We must be sure if our monitoring equipment are calibrated, are maintained. When we are talking about calibration, it means the value that we receive after the displacement value has to match with the reality in the pit. Your equipment must be calibrated, so we will assume that the value or the displacement shown by the monitoring is the exact data or the real data. We had a case of failure at Faulu 3, one of the mine in the central of DRC in the central of Africa. Faulu failure or Faulu mine is one of the mine of Tenke Fungurume mining, which is a copper and cobalt open pit mining complex located in the southern region of the Katanga province, DRC, approximately at 175 kilometers to the northwest of the province capital of Lubumbashi. The firm concession is approximately 1,500 square kilometers. The deposits are part of the Central Africa Copper Belt, a series of sediment-hosted stratiform cobalt deposits. Mining operation started in 2006 under TFM, Lundin Mining. The location of the 18 Planet open pit mine currently in the reserve is shown below. This is almost the location, and the failure occur at this complex where there is Faulu. As defined in Rock Engineer Mine Operation Practice, TFM's Rock Engineering Department monitors all F structure according to the associated level of risk. Rock engineering relies on satellites INSAR data provided by 3GV to monitor structure, either to remote for ground-based equipment. The rock engineer team reviews the data to identify areas which have started to move and where additional monitoring is required. In December 2015, INSAR supplied by 3GV indicated movement on southwest pit slope of Faulu Phase 3, the area which is in the green, but when you can see this area is the area where the INSAR shows a standing movement. After field inspection indicated increased movements, an IBS FM radar system was deployed on January 2016 to monitor the movement in real time, because the IBS FM provides reliable early warning for progressing slope movements, potentially leading to slope failure, and can map long-term evolution of moving slopes. In the mid-February, the IBS showed a progressive movement with high displacement rates on the same area due to the heavy rain. Many open cracks appears on the surface, and the inverse velocity graph predicted the slope failure on April 4, 2016. This is the prediction for the inverse velocity, and the inverse velocity predicted a failure on April 4, 2016. This is the photo taken in February of 2016, and the concerned area is this. Let me put. Okay, the concerned area is this area, and in March, this is the area, the concerned area showed by IBS radar, and in March, we observe a very fast movement very fast movement, and when we observe the very fast movement, some action was taken to make that area as a critical area for critical monitoring. And when we check the trend of the graph, you'll see like the movement becomes very, very high, and the speed become very, very high. This is the records, the data record on 11th of March. This is the second area on the same place, which is showing almost a catastrophic scenario. One day after, we observed that the trend of movement changed again, and the value, which is the value of the movement, becomes very, very high compared to what we observed one day before. And after observing these movements, we made the decision to close that pit because we observed that the movement becomes very, very high, and this was very dangerous for people to work under this area. And this is the situation observed in the field, and we send an email to our security guys to evacuate all the people working in this area. And when we can see, if you can see in this picture, you can see that there is many opening cracks, and the cracks are very huge. During the progressive excavation of Faulu 3, a failure occurred in the southwest wall of Faulu 3 on March 12, 2016 at 1449. The failed slope extends between 75 and 100 meters along strike and adds a height of approximately 45 meters, extending from the wide bench at the level 25 meters to the pit to at 80 meters. The failure was controlled primarily by structure and was exacerbated by talus material within the rats and the Jupiter breccia, and evaluated pore pressure due to the rain season. Cause of failure: a wedge geometry was formed by the RGS boundary faults, bedding that is parallel to the RGS boundary faults, and high angle faults. The interlamp slope angle at the time of the failure was approximately 26 degrees. This is almost the geology of that failure area. This is almost the displacement graph, shows a time series of that moving area, and in this area is the area where we record a failure. And what this is almost is the same things. What we can say here is the data received or recorded from the radars help us to take quickly the decision to evacuate the pit without having injury or without heavy death of the people or without covering equipment. And when we try to back to see why this movement increased a lot, we found that this movement increased because of the rainfall recorded in the February, and this confirmed why we record the failure early than which was predicted in April. This is almost the material, the failure material, and the failure records. And when you can see, our berm was somewhere here, and failure material went beyond our berm limits. All the people was evacuated, and we manage successfully this failure. And this is the presence of the talc, which contributes to this failure. In terms of remediation, TFM rock engineers and consultants recommend removing the failure material and creating a step out at the level 87 meters level. A rock berm was proposed before continuing the slope with the all direction perpendicularly to bedding. Back analysis of the failure slope was completed using the SWedge software. The geotechnical action plan for working in the failure area was implemented, and this is an example of the gap which was made to remediate that area. And in short, in this gap, we recommend to work under a radar, and the radar should work perfectly before to start any job in this failure zone. And in the case of yellow alarm, the geotech will check the radar data and will inform all the operation guy which should be the future action. And in the case of red alarm, all the people should evacuate. In conclusion, mining excavation and weather generally affects stability of slopes and hence requires properly monitoring even after providing the support measures, and especially so under complex and heterogeneous geology. From this study, the significance of the IBS radar system for high slope monitoring with high level of accuracy around the clock is well evident. The prediction of failure was possible based on the inverse velocity time graph, even for the prediction time for the failure was affected by the rainfall of February 2016 in this case. The alerts generated by the radar system based on the assigned threshold value and the regular evaluation of the radar data help in taking timely decision, thereby saving the men and the machinery working in the site from any adverse incident. Early detection enables proactive measurements, reducing the risk of loss of life and properties. This is the risk reduction. Alert seeker timely evacuation and implementation of stabilization techniques. Integrating early warning system into existing slope monitoring practices is crucial for enhancing safety and preventing disasters. Thank you.
So thank you, Freddie. We really appreciate it. Really appreciate it. A quick one, please, if anyone has any questions, you may type it in the comments or the chat section so that we can look at them and then forward your questions to the presenters and then they may answer them for you. So we really appreciate that, Freddie. Thank you so much. Quickly, next on the bill, we have Mr. Mr. Elisha Kanyembo. Please take center stage. Let us receive you.
Okay, thank you very much. Can everyone hear me?
Yes, we can hear you.
Okay, thank you. I'm gonna share my screen. Yeah. So thank you, gentlemen, for joining this webinar, this remote conference. So as I said, I'm Elisha Kanyembo from DRC, Congo, and I'm working for Kamoto Copper Company. So I will be sharing with you guys a case study for Cove Pit. We had a failure, and the Cove Pit is one of the biggest pit in Congo, I think in Africa, Central Africa, with a lot of challenges. So it's the most complex pit that any geotech can get experience by working in a Cove mine. So our Cove Pit got a lot of challenge in terms of water, in terms of weathering, in terms of structures, and so is an area, as I said, is really complex, and we are dealing with a lot of failures, issues here, and as a geotech is really a good area where we can work. So I will be moving with my presentation. So let me look for a pointer. So the agenda will be KCC overview, KCC Bilnos failure. So I will be presenting the failure itself. So the investigation we did when we had the failure, the impact to the plan, you know, most when we have a failure, so there is always an impact to the mine planning. The remedial strategy that we use to remediate to that failure, and what should be the conclusion at the end. So DRC in Africa continent, we are somewhere there in Lualaba province where we have that red dot. So Lualaba province in Kolwezi town, this is where KCC or Cove mine is located. And this overview, you can go into Kamoto Copper website. We can find all of these things that I put there. I do not want to waste your time. So straightforward on the Bilnos failure, the overview. So yes, you can see on my picture here, this is the failure that occurred in September 2023. And the radar system detects the slope movement from initiation until collapse. So it was really well managed or well controlled. The movement have been tracked by our radar system. The red alarms trigger, orange to red alarm, and our tap has been followed as stipulated in the tap. So as you can see, here I said 20 to 29 hours between the alarm and the collapse. So between orange and the red alarm. So there were enough time just to manage the evacuation. So enough time. And as I said, the effective tracking of progressive deformation and accurate collapse prediction, because we did forecast the collapse, and the prediction has been done using inverse velocity technique. And the collapse has been predicted to occur at 1:45, and the collapse occurred later, so 30 minutes later. So yeah, which means our forecast was really well done. So, and on this picture below, you can see that because of that prediction, we did evacuate on time and put barricades, so the exclusion zone. So we define the exclusion zone. So no access was allowed just close to the failure. So this is where the failure occurred from my system. And you can see how the failure occurred is just from 1350 to 1420. and overspilled material just flow down. You can see the run out of the filled material on the 1290 RL. So that was a wide catchment that contained filled material. Okay, guys, we went just back a little bit from the pre-failure observations. So this area didn't surprise us. So we were seeing some sign of instability. And when the shovel was working there, the radar was reporting some deformation within the completely weathered CMN unit. So as you can see here, there is some weak contact between RAT, CMN, we have RAT and RGS. So the contact between the different lithology is always weak. And in between the two RAT, so you can see there is this CMN, is a highly weathered CMN unit, just there, sitting there. And at the time we were just inspecting the area regularly as our routine on visual inspection. So we could see some bench scale failures, some cracks. So you can see like this one, this area, the bench scale failure occurred here, and extended tension cracks. So the area was showing sign of instability. As I mentioned here, I said several instability on individual benches were observed. And visual inspection on the failure when the day of the failure, when the failure occurred. So you can see that I can say the left hand, my left hand side, the one that I highlighted in black. So this area was, after the failure, it was like the backscape that was steep. And it was just unraveling time to time after the failure. So the block was a block hanging at the top after the failure. So it was potentially the material that could fail again. And linear deformation trend was just being picked up within this area after the failure. So this area was not showing further movement because it failed already, but this portion, this block was showing further deformation. So this is what to worry us about, because you can see on top here, there is a main road or main access to the northwest dump that was affected, because we've seen even some extended tension cracks just behind the backscape. So, and then quickly I said, okay, this is the failure timeline. I could just present it to you guys the way we manage this failure. So, because I can share with you guys some confidences. Since we had that fatality in 2016, so we were using a radar system, but the problem was the communication that was also problematic at that period. And after that fatality, so I just give myself a commitment that it will not be possible as far as I will be waiting for KCC to have another fatality, because as a geotech is really sad when you are working as a geotech, you are preventing, you have to prevent this kind of catastrophic event, but the main purpose is just to save life. And if you fail to save life, this is not something that you can appreciate in all your life, because that one will remain and you can all time remember that, so it is not good. But here we can see that we follow the process. In June to August, so slow linear movement was detected on the slope from our ground base radar, which is the IDS radar, the one that we are using. And we can see that in July, increase in velocity And that one was just post big blast. So as a geotech, you must know that blasting can induce some instability into the oil if it's not well controlled. So as a geotech, we need also to look at the blast design so that we can ensure that there is no energy release that can be propagated into the slope benches and create some instability. But this was a big blast that has been conducted, and we've seen that just after that big blast, some movement has been detected, so increasing the formation within the slope benches. And in September, the orange alarm, so 7th of September, it was around 8:15, orange alarm, and the area below unstable area clear. So we declare that the area below was an exclusion zone and barricaded off because we didn't well demarcated the failure. And we say, okay, below the failure, so exclusion zone. And when we had the red alarm, so even the ramp above, so you can see on that previous image, I mentioned that there is a main road or main ramp to the north dump that we are using. It was just adjacent to the failure. We closed that one as well. And after that red alarm, a very strong progressive deformation trend, and we did the prediction for the collapse at this time. And the collapse occurred. You can see that the prediction was 1:45 and the collapse occurred at 2:15. So just 30 minutes later, which is fantastic. And after that, Geotech recommend opening a single line. Because after the failure, we went there and we check. We say we didn't see any further, or I can say extended tension cracks on that road. We say, okay, preventively, we open just a single line at the top of the failure. By opening the single line, after that, we've started seeing those linear deformation trend reporting within that hanging rock mass. And we say, oh, this is not good because it can just extend it more. On the ramp, as we're gonna use big tracks as we use in our mine, that can also induce more deformation. And Geotech, it was in the morning when we went there for the site visit, and the Geotech instructs to close the ramp because the progressive deformation also was just start being reported. And on 11th of September at 12, additional material came down on the failure. So that hanging rock that left from the initial failure, that one also failed. So this is the way that I can say we manage this by closing. No one was exposed under to that risk. So the area was completely evacuated. No one was exposed there. Machinery evacuated, so there was no injury, no property damage. So this is a slope stability monitoring data. As you can see, we plot some pixels on the data, but here, as you can see, you can see before the blasting, the big blast, the movement was just a normal, so the area was stable. So after just the blasting, you can see the change on the deformation trend. So this shows us that the blast induced instability within that slope. And up to the failure, so the movement was well tracked and everything was well managed according to our TAP. Okay, so now the failure investigation, the failure occurred. So it happened. So the work of a geotech didn't stop there. we must now investigate what was the failure mechanism? What drive all of this instability? What was the issue? So this is what a geotech has to ask as a question himself. What was really the main issue? What caused this failure to happen? Because the design has been done, and the review, analyzed, and we provide all what's supposed to be done, but how that the slope didn't stand. And you can see here that is the top benches that failed, and the failed material just overspill on top of the bench below, and go and fill the 1290 RL. At the two sections, they are showing almost the same situation. But we went through and investigate on the failure mechanism. So we have borers within this area. So we checked some borers and some logs, and we found this Cove 1085 borehole. This one, because this is the failure where the failure occurred. And we found that the failure surface aligned with the initial, the hypothesis that we were just investigating, and say the instability is driven by the that contact, CMN rat contact. So the location of this contact will determine how far back the stability can extend. Because we said, okay, let's look at this data. And we check also the TECT model, and we found that this contact is not in the TECT model. Because this CMN here was locked not as a CMN, but as a saprolite. This was also the mistake, because when we did the model, we analyzed the design, so we didn't take in consideration that we have CMN talc within this contact. So it says saprolite, so it's different with CMN talc. And the confidence in orientation, etc. So we found that, and we say, okay, in this case, let's drill some additional holes within this area, just to try to demarcate the extent of this contact of CMN with the rat. So we should normally, first of all, understand where is the contact, so that, because we know that that contact is the weak contact that has driven the instability. And after that, that was the geotech assessment, etc. We drill, and we try to understand all of that, and we demarcated the contact, CMN and the rat. But the impact to the plan, what was the impact to the plan? Imagine at the top here, so there was the main access to the North Dump. So the North Dump is the biggest waste dump in Cove, where all the waste from the mine is being just dumped. So this access is at the top of the failure, so was closed, blocked. We could not send, in the meantime, waste material to the North Dump. But we had the other dump is Mashamba Northwest Dump. So we could just send waste to the Mashamba Northwest Dump, with the risk of filling this dump faster than planned. So you see that was the impact to the plan. And also the impact to the plan was also on reduced ore ton and the copper content in 2024. So it has been in the impact even to the production of copper content in 2024. So related to that one, we said, okay, let's make some new ramp design. So you see there is this blue one and the white one. The blue one was the temporary. So a temporary access or temporary ramp, because this is our area of concern, and we say, okay, let's shift a bit the access to the north, And the other option is this white one. That could be the permanent. But within the same area, we have pole lines, so electrical pole lines. So I think within the same area, the power line and also the relocation of the GCI North power line. So we have power lines here. So they were the constraint for the new access. Anyway, and what we said, okay, the remedial strategy, as you said, there is this access to the West Dump. There is a design that, first of all, we said, let's clean up. There is a cleanup of the catchment below, and there is a back cut back design, all of them. So we found that to remediate to this situation, let's have a temporary access. Let's try to clean material that filled our catchment below, so on 1290, and let's create an access here on 1350 so that we can stabilize the area. So all of these things were just options, okay? And definitively what we did is clean up of filled material. We clean filled material that I can say what I said, overfilled material, overspills material on 1290 RL. So we clean that one. We put a risk assessment together and we clean safely. And we said, let's go and establish that the catchment, the bench here on 1350. So for this one, we didn't succeed because we failed to make it. The time we were doing that, material, the hanging material on top was just falling down. And we abandoned that option. We moved to the cutback option. So this was the proposed cutback, and this is what we did. So the design of a mini cutback, and we mine with this design, and this design took in consideration the drilling we did to demarcate the contact of CMN and RAT. So we did that, and the cutback design took in consideration that one, so that we mine all the CMN and we leave the slope only in RAT, which is good material for us. It's not that good. I told you that the weathering here in Cove Mine is really high. So fresh rock, yeah, is the language that we are not talking here, fresh rock. So, but we have only highly, moderately, and completely weathered material. So we went with this mini cutback, and we cut. It was a good work under radar monitoring. So all the work, the remedial work, has been done under good supervision, and so visual inspection and the radar monitoring. Anytime there were a movement, so we stop activity, we do visual inspection, we amend the recommendation, etc., up to where we finish the work. So you can see this is the mini cutback that we did, and we clean up all the failure. So you could see the difference between the failure picture that I started by during my presentation and this end picture, the last picture. So this is the, I can say the remediated failure. And right now you can see that we establish all the benches up to the 1350 RL, and we continue with the normal design, what I call Cat 5A1 final mining, progressing. Actually, so this is an old photo because now we are on 1280 RL. So we continue with now the normal design. And the area at the back is stable, sitting, no further movement within this area. As you can see, We did even slow movement analysis. The subsampling have been done. Imagine we took 5-month data using 2 scans per day, and the subsampling is showing us 42 millimeter maximum in 5 months. So that means the movement is a very slow movement and nothing to worry about for now. And we have this AXA which is monitoring that area. So guys, this is the end of my presentation. The key takeaways for you guys, the one that I can think that you can remain with is proper management of a structural control failure, like this one for COV Cat5 A1B nose failure, by using slope monitoring procedure, interpretation of failure mechanism, and remedial plan. So the proper management is using the monitoring procedure properly. You must have your tap. So your tap must align with your site. You can't copy my tap and use it in your site. So every specific site must understand the failure mechanism of the area by doing back analysis, and you come up with your threshold for your alarms that match very well with your site. And this is what you're gonna put in your tab. And you must very well interpret your failure mechanism. So proper code logging, face mapping, you understand all your structure, etc. And you must come with a good remedial plan as a geotech. The second, use of post-failure monitoring as part of the failure remedial plan. So post-failure monitoring can guide you if you are in the right way or wrong way. And you can stop anytime and change direction. So you must continue monitoring your slope when you are doing your remediation. And the last one is the mining companies. So if we are not putting money for buying technology for slope monitoring, so that is not a good practice in the mining. Actually, the technology is helping us for safe mining environment. So technology like radars, so radars, as Freddie mentioned, early warning system. So the early warning system is really helping us to save life. Otherwise, it will be always late that you could see the failure, but it will happen and it's late because you do not have an early warning system for your mine. Thank you very much for your attention. This is from Elisha, KCC Mine.
Thank you. Thank you. Thank you so much, Alicia. We appreciate that. And to also continue, if there are any participants with questions, please leave them in the chat section and we will come back to them and then answer all your questions. Quickly, I will also move on with my presentation. Okay. All right, so my presentation is going to briefly be about Guardian integrations, where we try to understand the integration between the radar and other GNSS technologies like the TPS and the GMX and all of those other systems that we have that are typically used for long-term monitoring. And so this is a brief about me. I'm responsible for mine monitoring solutions in the West Africa region. and I'm the sales commercial engineer. And so those are my details down there. In case you need to reach out to me, feel free. Now, about mine monitoring, what essentially we are doing is to be able to combine the two foremost technologies that we have. That's from the IDS GeoRadar and then the Leica Geosystems geomatic and geodetic monitoring systems. So essentially, what you will find is that all across your mining operation, as you may have, we have different systems that do various different things in different capacities to be able to help you manage your entire project or entire operation. So from your far left, you can see where we have the satellites, INSA satellite systems where we are able to monitor remotely and be able to send and provide reports to you to be able to do your monitoring. We also have the GNSS systems and the GNSS antennas for long-term monitoring. And then we have the fleet of radars where we have the IBIS FM Evo, the IBIS Rockspot, the IBIS FB, the Hydra X, and then the IBIS AXA, our flagship radar system. So all of these systems form the part of the interferometric radar systems. And then we have the geodetic sensors where we have the Leica Nova TM60, and then we have the Leica Nova MS60. They have some very slightly different functions which can allow them to monitor different campaigns long term. And then we can sum it up with the Geo Monitoring Hub software, which combines all of these instruments that we are seeing here and allows you to combine the data and have one concise data platform where you can review and analyze everything that you are picking up. So quickly, we will be looking at two sections of the Guardian integration where we have the FPM 360 monitoring integration, and then we also look at integration with the GNSS sensors. And that right after that, we will quickly look at two case studies where these combined applications have been used or utilized. So the FPM 360 basically is a system that allows you to combine multiple radar systems, multiple IBIS radar systems. So we can have two radar systems being combined or even three, as we can see in this example here. And all of them can be done using the IBIS master license or the IBIS FPM 360 license for multiple radar systems. And so this is basically what the architecture looks like, where we have different radar systems talking to their processor systems, typically in the office, and then all of that data is consolidated onto the data server, which can be then accessed with the FPM clients for analysis, or you can have the Guardian Master FPM, where you can set your alarms and then set all your thresholds and make sure that you are receiving real-time data. So in a nutshell, this is what we expect it to be able to do, so that the processor FPM receives the project from one of the radar systems. One of the radar systems connects to one FPM processor, so that in this case where we have, for example, an FM, what it can do is to show you the maps. You can create points and areas and time series. But what it cannot do is to create a hazard map or create a hazard time series, and it cannot export data. Moving forward, the master FPM will be able to combine them, two different systems, and then create one huge map for you where you can be able to visualize the maps and the time series. You can import and export data, and then you can create and set hazard maps and hazard time series. Once that is done, you can visualize it in different sections, whether you want to visualize one at a time, like we have at the bottom here, or you can decide to visualize both of them from the top, like you can see here. And you can also open them into multiple windows for different monitoring scenarios that you are observing. Like we rightly said previously, what you can do is to be able to do the hazard time series or just the regular time series for analysis, and you can be able to plot points and do all manner of analysis with it. And once you want to set your alarms, you will be able to set the alarms for even individual radar systems, as we can see in the picture. So it will be possible to set different velocity thresholds under the same rule, and it's also possible to disable a radar unit if you don't even want it to appear in the alarm. You can just do that by clicking on the squares right beside them and disable them. What this also allows you to do is to, because in combining them, it allows you to visualize your data in 3D. What that does is that it allows you to see the vector. You can see the vector, the direction, and then the magnitude of the areas that you are monitoring. You'll be able to see the direction in which it will fail, for example, if that is what you are looking to see. It allows you to do that because that data then becomes a 3D data, and it gives you the magnitude, the direction, and all of that. And once you are able to combine them, if there are any overlap areas which ideally should be able to properly give you the exact or the correct vector diagrams that you're looking for. In this area, for instance, you should see that here and in these areas. And in cases where you have even 3 or more than 3 or 4 radars, you can see multiple overlaps, and those areas are even more accurate with that. And it is only the IBIS radar systems that are able to do that currently. All other radar systems on the market are not able to do that. We will quickly now look at how to integrate the data with the GNSS systems. Basically, what that means is that if you have a TM60 and you want to be able to combine the data with an IBIS AXA, you can plot all of that data onto one DTM map, as you can see in the picture here, so that you will be able to compare the results that you are getting from the radar and juxtapose it to the results you are getting from your TPS or your GNSS system. In order to be able to do this, what you will need to do is to get an APN, which is a license, and when that is installed onto the computer for you, it allows the two systems to talk to each other. To be able to do that on your project pane on your Guardian software, at the bottom you should see Prisms and GNSS. Once you click there, you'll be able to see import. Once you click on that, it will connect to the GeoMOS system and then import all the prisms in here. Once it imports the prisms and you allow it to show on the map, this is what it should look like. So in this case, this is an example of a mine that is showing all of their prism systems that has been installed onto the same pit map. With this done, it allows you to visualize the data, so you can plot points on the map and then analyze it together with points that you are receiving from the TPS and or the GNSS system. So you can create custom maps, custom time series, and all of that to be able to do your analysis. This also gives you the opportunity to be able to see your line of sight vector. What that means is that it will be able to project it in 3D for you. So just like we have when you combine multiple radars, this one will also allow you to see the magnitude, the direction, and all of that with the GNSS system. And in that same case, you can see the vector graph here, where we have the X components and then the Y components of different portions that have been plotted onto the maps. So quickly, we will look at the two case studies like we mentioned from the beginning. So the first one is a pit wall failure that was detected through early detection monitoring, and then the geotech analysis that were done as they tried to do two stabilization batteries. And this was in BHP, Australia. So a quick background, BHP's Australia Iron Ore, they have 5 open pit mining areas in the Pilbara district. And each of these pits that they have is within 100 to 200 meters. Now, these pits use single and double bench configurations with butter heights of about 12 and 24 meters. Now, the case study focused on the early detection of post-blast movements in the pit wall, leading to a geotechnical back analysis and remediation design. So going on with that, they were able to model the slope behavior and communication with the other teams that were involved in the mining, and then their trigger action response plan, they were able to remediate the entire problem that they had. Now, we will look quickly at the lithology that they have there, which is a formation of the Petrozoic Hamsley group within that Pilbara region. That is predominantly what is there. And this consists of thick detrital sequence made up of red ochreous material and tertiary channel deposits. What that means also is that it's mainly siltstone, gravelly siltstone, and vaggy breccia, which are prone to rock mass failure due to the soil-controlled nature of the material. At the base of the slope, the exposed West Angeles member contact units overlay the Mount Newman member. So it explains why, this shows to explain that there are different lithologies overlaying each other, which makes it very prone to failure. Now, their monitoring setup that they had as at the time of the event, they had INSAR data coming in. They also had PRISM monitoring data, and then they had the IBIS radar system. They also had VWPs to aid with what they were doing, but then they realized that the water pressure was not a concern as the water level was more than 30 meters below the pit floor. And they also had some other services, the 24/7 monitoring services, which allowed them to monitor even more accurately. So in brief, this is what it looks like in terms of their monitoring setup. The Tre Altamira supplied the satellite system or the satellite data, and then they had the ground-based prisms from Leica, and then they had the radar systems. And so on the map here, you can see where they were interested in monitoring. They had VWPs mounted across. Then they had the 2 radar systems sitting adjacent to each other on the walls here, and then they were monitoring. So you can see the small triangle here showing where the VWP was installed. So after an in-pit blast, that's blast 1, the slope exhibited an initial linear deformation with a 10 millimeter relative displacement in the first 24 hours, and this was recorded by the radar. The deformation rate then slowed, showing a regressive trend with a displacement rate of 1 millimeter per day over 3 weeks, totaling around 20 millimeter of movement. Following this, alarms were adjusted and the movement further regressed to about 0.7 millimeters per day. And then the BEM loss occurred due to weak wall materials, like we mentioned earlier, because of the lithology that was there. So when mining cuts past the center of the movement area, a 50 millimeter displacement occurred within 24 hours, leading to a temporary halt in mining. After resuming operations, the displacement rate increased again to 3 millimeters per day for 3 weeks straight, then slightly regressed to about 2.5 millimeters per day for 2 additional weeks. So throughout, the geotechnical inspections were done, radar monitoring also continued. They didn't stop there. Okay, so 3 weeks after mining, a second blast, which is blast 2, occurred 300 meters from the movement area. Initially, there was no radar or prism change, but 7 days later, 10 millimeters of displacement was recorded within 12 hours, cracking up to 50 millimeters behind the pit crest prompted closure of the area. So as we can see in the photos there was cracking at the top of or at the crest of the wall. Some cracks showed 300 millimeters dilation and were linked to kinematic buckling from stepped excavation. Now, after 65 days post-blast 1, like we saw in the previous slide, with 135 millimeters total displacement recorded, the radar and prism data revealed through progressive slope movement towards failure. Now, although velocity changes made predicting failure difficult, stepwise increases in velocity indicated impending failure. Okay. A detailed slope model assessment began after the closure. So we will see that here, 65 days after the initial movement from blast 1 and 30 days after the mine was completed, total of 135 millimeters of displacement was recorded in the central slope area. So all these areas that have been created here were analyzed, and then they found that an average of 135 millimeters was recorded within the entire period. So they could see the failure coming down from the top bench there. And so you can be able to see that in the analysis that was done here. Now you can see blast 1, which sort of triggered the entire sequence, and then blast 2, which sort of made it to go all the way through. And you can see other triggers that were observed in this areas here. So the displacement graphs showing velocity changes triggered by the blasting. And so if you correlate the data that was also done by the prism monitoring, you can see how it's correlated, and it was going through like expected. So they could determine clearly that it was the blast that was triggering all the accelerations that they were seeing in the movements. And so, in summary, the prisms were able to find that they had about 0.9 millimeters per day in movement. The radar also detected 0.068 millimeters per hour. And then the satellite data, which is the INSA, about 7.5 millimeters per month. But then these were also the peak detections that were done. And so you can also see when you juxtapose all three, so we have the INSA data, then we have the prism data, and then the red one is the radar data. And so you can see how they somewhat correlate, and we are able to determine what is happening is consistent. Now, so in analyzing the slope failure, finite element analysis was conducted using a modified geology model. Now, the model was robust enough to evaluate current and future conditions of the wall. Okay, so the maximum shear strain function demonstrated instability at 3 stages. That is the existing slope, 1 additional bench, and 2 additional benches. So as you can see, the instability was just going through all the stages. Now, in remediating this, there are 3 geotechnical options available as according to the National Resources Conservation Service 2005. So it is either you unload the crest, which will reduce the active driving forces, or 2, you reinforce the toe of the slope, which will increase the resisting forces. And then 3, you allow the failure to safely occur, and then you remediate the outcome. Now, the operations determined the buttress needed to be 20 meters wide for operational purposes and 60 meters high to stabilize the exposed fault and minor failures. Then the analysis also compared maximum shear strain in the original design versus the buttress design. After confirming it met safety criteria, the buttress was approved for execution. So this led to a revision in pit design to accommodate the buttress, which will span 550 meters in length and use about 689,000 tons of waste material. So that was what was done. So you can see the area of instability and then the direction of the buttress that was constructed to be able to stabilize it. Now moving forward, the buttress construction began 135 days after blast-induced movement with a cumulative displacement of about 260 millimeters by that time. So the radar was also able to track the buttress effect, showing progression from east to west, like we can see in the photo over there. Red areas on the radar indicated sections not yet covered by the buttress. A butter scale failure caused by changes in stress was detected and monitored. Meanwhile, regressive movement was also noted as the buttress advanced, though interference from the tracks and thus affected radar readings in fully buttressed areas. So you can see once the buttress was added, there were changes in the progressive movement that was earlier seen. And so if you move forward with that, you can see that area of instability that was observed, and then you can see the area of field material, the buttress progression and all of that. And you can see relative stabilization after a period. You can see the same thing on the other side as well. Now, when that was compared to what was done with the PRISM monitoring data, you could see the regressive movement that had started trending, and you can see that also on the radar data along this section. So long-term displacement rates showing the slope stabilization and post-buttress construction. Now, in review, they also attempted to verify what was seen at the beginning. So at the beginning, this was what the radar was seeing pre-buttress, and then after the buttress was fully constructed, we could see that it had stabilized. And this was also confirmed using the INSAR data, where we could see the area showing all these red dots here, which is how the INSAR data shows. And it was showing a deceleration trend as it moved ahead in time. And so in conclusion, the slope radar technology enabled them to be able to predict and prevent the slope failure. And they've also updated their TAP, and now across BHB sites, since this was key to their success, they rely on the radar theory and their alarm limitations to be able to work in the safe environment like they expect it to be. Now, I'll quickly move through the last one because of time. So this is a mine in Brazil, the J. Mendes group, where they have both the IBIS system and then the TPS system. So quickly, this is what they had their pits looking like at the beginning of the monitoring event. But then as it progressed, they had the TM50 and then the Hydra X measure some cracks in their walls. And so you can see that in the next slide here, where they had an area that was moving rapidly. That had gone beyond 20 millimeters per day. And so they could see that the area was. So by integrating the data, they were able to see. So this is the AXA that they had, and then this is the TM50 that they had that was monitoring. And so they combined this data together in this software, which is the Geo Monitoring Hub software, and we're able to analyze. So you can see at this section here, that they have movements going on. Sorry, you cannot see my pen. They had movements moving in direction. And so you'll be able to see the direction, the vector of the area that is being monitored or being analyzed. And so that was how they were also able to manage their operation or manage the failure that they were having in that operation. Unfortunately, because of time, in case you have any questions, please type them in the chat, and then we will be glad to get back to you on them. And quickly, next on the bill, Augusto will take us quickly through the recent developments and recent things that we have.
Maybe Bilson, I was considering, thank you, Bilson, great presentation, and thank you, everybody. Maybe I was considering, because it's already 3:30, so we are basically at the end of our webinar, why not, instead of rushing with my presentation, that it's a lot of content, I can send the presentation in a more complete version by email, and then you can feel free to reach out to me by email if you have any question, because I think it's also important now to dedicate some time to your question, to the real case studies, to Freddy, and also to Alicia, and also to the Bilson one. So probably, if you agree, Bilson, I think instead of rushing, let's take these last 10 minutes, 5-10 minutes to listen to the question and then wrap up the event. And I will share my presentation by email. That, by the way, was about our recent releases and a presentation of Ideas Generator. So probably we will consider next webinar to be a little bit longer for the future, because we are planning to arrange more and more of these live events. So this was a very first attempt, we can say, and I think it was successful. Many people attending, great contents, and I really would like to thank Freddy and Alicia for taking their time to present really amazing presentations. So if you agree, Wilson, let's go check the questions and maybe let the
right.
presenter answer.
Okay, that's fine. So I think Mohammed Lemin had a few questions for Mr. Freddy. Mr. Freddy, can you quickly maybe unmute? Okay, nice, Freddy. So I think he had a question, 2 questions for you. I don't know if you can see the chat, otherwise I can read the questions for you.
Yeah.
Yeah, you can read the question.
Okay, so first question was question about the tap used for this failure. How many red alarms before the failure, and how did they deal with monitoring on night shift? And the question number 2 is how often the tap gets updated. So first question, how many red alarms before the failure, and how they deal with monitoring on night shift?
Okay. About the trigger action response plan used, we started with the 2 thresholds, 7 millimeters per hours for yellow alarms, and 9 millimeters per hours for red alarms. And this TARP was set up for the beginning of the movement in that area. And when we observed that the movement, we record the progressive movement in that area. The TARP was changed to 3 and 5 millimeters per hours. I can say we have in the past one as a trigger action response plan, 7 and 9 millimeters per hours. And with the progressive movement recorded, the TARP was changed to 3 and 5 millimeters. How many times we record the red alarm? We record the alarm 3 times. The first time it was on 11 of March when we record the red alarm, but this red alarm was not stopped after few minutes. And the second, it was in the midday of the same day. We record another red alarm, which stopped just after after 1 hour. This red alarm stopped. And the third red alarm was recorded 1 day after. We record another red alarms, and with this red alarm, we recommend to when the first red alarm occurs, we evacuate. And we inspect the area. And when the red alarm stopped, we mark that the area, and we recommend to the people to not working in the vicinity of that area, close to that area, and work at the other area. And when we observed secondly the red alarm, this area was already barricaded. The next day, when we record the same red alarm, we try to adjust our BEM area, the area where we put in previously our BEM. We try to adjust it because we found that the area becomes like very large, and we try also to enlarge our BEM safety. About the night shift, in the past, our all monitoring screen was in the dispatch, in the mine dispatch, and in our procedure, when they record the red alarm, normally in the night shift, they have to evacuate. This is what it was recommended. In case they receive the red alarm in the dispatch centers, they have to evacuate. And if they record like yellow alarms, they have to call the geotech who was on duty or was on call. The geotech can check the data shown by the radar and advise. This is what we did in the past during the night shift. But during the night shift, we can stop. In case we have a red alarm, it will recommend to stop. And the daylight, we can check the area and try to manage which area is affected and which area we can close and which area we can resume with operation.
Yeah.
Okay, I think.
Yeah, I think that's.
This is
otherwise maybe the last one.
Yes.
How often the TAP gets updated?
Yeah, I can say is just normally what I can say, normally the TARP, the TARP or the threshold are subject to change based on input from the rock engineer department, because the behavior of movement of the rock is not the same. We can find in some area, with the small movement, we can end up to the failure. And in other area, we have to record the big displacements, which can end up to the failure. And the TARP can be adjusted depending on the type of the rock and the movement behavior, which is recorded in each kind of the rock that you have in your site or we have in our site here.
Yeah. Okay.
Thank you.
All right. Thank you
I
so
see
much.
we
Fred.
have a comment also from Mr. Senga about I have a question concerning the geology, but maybe if you are still there, if you can be a bit more specific. And this question was addressed to Elisha.
Yeah, Lorenzo, as you said, so if he can clarify his question so that we know exactly what he wants to understand on the lithology.
Yeah, maybe. But I don't know if he's still there, but in the meanwhile, I think if you maybe, Patrick, you can type your question more specifically. Otherwise, if you're still there, later we can enable your microphone. And then we have a question from Mr. Abdallah Bula. Do you have new upgrade for the system of new tools to help for the prediction of failure time? So this is for us, basically. And well, so we can take this question, Bilson. Maybe I can start. At the moment, the main prediction tool for failure time is the inverse velocity we are using. So this is quite, it's a common tool. So it's based on, statistics, and it works quite well. But at the same time, we all know it has some limitation. It works good when there is a progressive acceleration, a progressive failure, going to an hyperbolic trend. What I can tell you, there are developments for new tools, so different tools than the inverse velocity. I cannot tell you when this will be implemented in the radar, but I can send it to you even by email. Just let me collect some papers. Some of these papers were presented at the latest slope stability in Brazil this year. So that there is something happening even on this direction. So I think soon this will be even implemented in the next software version. So I don't know if I answered to your question.
Yeah, I think, so we will, there's some data or information that is coming up soon, and we will try to send an email across so that everyone gets that information as well. To quickly with the announcements, so this is the first in the series of webinars that we'll be conducting. We intend to have them at least once every quarter next year, 2025. So you can expect more of these kinds of webinars and works going on, so that we can help you to be able to do much more, even with the instruments and then the instruments that you have currently. So we will continue to do these webinars next year. There will be more of them coming. We will send you emails to notify you and all of that, and so that anyone who wants to join will be able to learn from them. So we will quickly bring this to a close. Thanks for spending the extra 10 minutes with us. We really appreciate you spending the time, and we hope to see you in our next session and our next vision. Thank you so much. Wish you all a very wonderful day. And thanks to the speakers, thanks to the guests who made the presentations. We really appreciate you. Thank you so much. And
I think maybe so we can
there are some more
send
questions coming, so we will answer them. We will send you emails on them. Thanks so much, everyone. We really appreciate it.
And also this is all recorded, so the idea is to share the recording with all participants, and we will also understand. Well, I will, as I said, share my presentation that we didn't have the time to show today, and of course we will share also the presentation allowed to share. So I would like also to thank you one more time, and soon you will receive information for the incoming webinar. Let's say for 2025, we will define some specific topics to develop our webinar, and maybe the idea is to create a sort of periodic mining monitoring talking, so where we can bring us new ideas together and having good discussions like today. So thank you again, everybody, for the contribution.
Yeah, thank you. And we see some questions still coming. Please, we will respond to all of them in your emails, so do not worry. If you still have questions, you can type them. We will respond to all of them and send you an email on them. Thank you very, very much.
Thank you.